And my advisor is Riyad, Aboutaha. My research is about the rehabilitation of concrete structures. And today, the title of my presentation is Bond-Deteriorated reinforcement in concrete beams, stressed with CFRP. So, corrosion is always a headache problem for engineers. And most engineers always try their best to avoid the corrosion of reinforcement and find some ways to rehab the concrete beams with corrosion. So corrosion of reinforcement usually causes reduction of cross-section, spalling of concrete cover, deterioration of bond between reinforcement and the concrete. A lot of researchers have done research with all of these factors, but nobody just consider only one of these factors. So about the deterioration of bond between reinforcement and concrete. So I did some research about the deterioration of bond between reinforcement and concrete, and then use CFRP to rehab these deteriorated concrete beams. So the picture shows the corrosion of reinforcement, and we can see the concrete, the spalling of concrete cover from this picture, and some rust on the reinforcement. So I designed some finite element analysis models, and the blue means unbonded lines, and the red in this picture means CFRP. I placed the CFRP plate at the bottom of the concrete and to increase the flexural capacity, and to CFRP anchorage at the two ends of the beam to avoid the bond failure. And since I just want to do the research about the flexural capacity of the beam, so the stirrup spacing is very small, just 250 millimeters. And the shear span to depth ratio for this beam is 6. The length of the beam is 7,000 millimeters, and the depth of the beam is 500. Since when I talk about the shear span to depth ratio here is 6, since I want to do some further research about the shear failure of the beam. About the effect of unbonded lines for the shear failure of the beam. So all the beams were reinforced with 3 number 19 deformed steel bars as main tensile reinforcement, and 2 number 10 deformed steel bars as top reinforcement. The tensile bars were anchored in the test span using a stand hook to prevent anchorage failure. And the steel stirrups were also number 10 deformed bars with 250 millimeters spacing. Yield stresses of steel reinforcement were 414 megapascal. So there is the first picture is a parameters tree. There are total 16 specimens, and the table is the summary of the specimens. So we can see the first column, the R1 T0. R1 means the reference beam, and T means thickness of the CFRP, and 0 means zero thickness of CFRP. So, and U means unbonded lines. 15%, 15 means 15% of the unbonded lines, and 13% unbonded lines, and 45% unbonded lines. And the thickness of the CFRP is 0, 1, 2, and 3. So when we do the simulation, the most important thing is the property of the materials, right? So the first is the compressive behavior of concrete. I used the compressive behavior of concrete recommended by the Young. It's Young's model. It is a very popular model when we use ABAQUS to simulate. So for this model, we can just know the strength, compressive strength of the beam of the concrete, and then we can use all these equations to calculate every point on this curve, and we can get we can get the elastic stage, and we can get plastic stage, and then we just need to enter all the data into ABAQUS, and we can simulate the compressive behavior of concrete. After the compressive behavior is the tensile behavior of concrete. I used this model recommended by Nail and Rashid in 2006. Why use this model? Since this model, you don't need to consider the bond slip between reinforcement and concrete. That will make the model be very, very simple and avoid some convergence problem happen. So for this model, you just need to know the tensile strength, and you can get all the points on this curve, and all the parameters are listed like the R sub t, P sub t, S sub t, and F sub t is from the experimental results. So next one is the stress-strain relations of reinforcement. According to CFRP model code 2010, the actual stress-strain diagrams can be simplified by an idealized characteristic diagram. So it is a horizontal line after the reinforcement yielding. So for this table is the material properties using in ABAQUS. So when we do the simulation, we need to select the element type. So for concrete, I used the solid element, so it's C3D8R, and for reinforcement, I used the trash element T3D2. But since I need to simulate the unbonded between concrete and bottom reinforcement, so I used the solid element to simulate the bottom reinforcement C3D8R. And for CFRP, I also use C3D8R. But some researchers and some simulations online use the 2D model to simulate CFRP. But here, why I use 3D? Since I want to use different materials in the future to rehab the beams with corrosion like steel plate. Since I need to simulate steel plate with solid element, so I just want to keep the same element. So I use C3D8R to simulate the CFRP. And for the epoxy, I use COH3D8. And for all the elements, the second is the modulus of elasticity. And for concrete is 24 and 511. And for reinforcement is 200 and 1,000 and CFRP 164, 1,785. So for epoxy is 4,500. And the strength for all these materials, the first is concrete is 21 megapascal, and 414 for steel, and 2,800 for CFRP, 30 for epoxy. So this is the model I used in ABAQUS. So the first picture is the boundary conditions and the loading. The composite system was simply supported. So displacement in X, Y, and Z direction were constrained with pinned support. So U1, U2, and U3 is equal to 0. So to model the roller support, displacement in X, Y direction were constrained. U1 is equal to U2 is equal to 0. And to avoid the load concentration and the convergence problem happen, the external loads were applied in Y direction at pressure on a rigid load plate, which was tapped with the concrete surface. And for the other interaction, like the steel plate at the bottom and steel plate at the top, I used the tie interaction. And CFRP, epoxy, and the concrete, I also use the tie. So how to make sure my simulation is correct is the verification. I used the experimental conducted by Shaolin Manual studied to investigate the role of shear span to depth ratio for the cross-section area of RC beam on the deflection in RC beams, like the dim and normal beams, when the value of shear span to depth ratio is equal to 1, 2, 4, and 3. So in this study, TP number 1 was selected to verify my model. So from the curve, we can see the simulation result is very close to the experimental result. The load, the cracking load is and the ultimate load is very close, right? And second one, I used this test on one control beam. And for corroded beams, it's about the corrosion verification. And we can see the simulation result is also very close to the experimental result. So that means my simulation is exact and correct. So based on the simulation, and I can get the results. So for the first chart is a reference beam with different CFRP thickness, and we can see from the chart with the increasing of the thickness CFRP thickness, the strength of the beam increase, but the ductility decrease. And the second one is the beam with 15 unbonded lines, and also with the 0, 1, 2, 3 CFRP thickness. And the third one is 30% unbonded lines. Last one is 45% unbonded lines. And we can see the same trend with the four of the charts. And next chart is the same. I used the same CFRP thickness, but use different unbonded lines. And from this chart, we can see with the increase of the unbonded lines, the ductility decrease and the strength of the beam also decrease. So it's also the same with the 1 millimeter CFRP thickness and 2 millimeters and 3 millimeter CFRP thickness. So the conclusion, based on the results of the role of unbonded lines and the CFRP thickness conducted throughout this study, the following conclusions could be drawn. Unbonded lines of main reinforcement has a significant impact on the behavior of flexural dominated RC beams. For flexural dominated RC beams, the lack of bond between concrete reinforcement greatly affects the stiffness, ductility, and ultimate strength, all decrease as the unbonded lines increases. So CFRP is an effective rehabilitation material for RC beams with different unbonded lines. With increase of CFRP, thickness, the stiffness, and the ultimate strength were all significantly increased, but the ductility decreased. So that's all the references I used in my research. So that's all for my today's presentation. Thank you so much.